Hello everyone, I am Dr. Abha Kumari from Nirmala College. Today we will find the analytic function by using some method. There are two methods of finding an analytic function. So today we will discuss about the first method. How can we find the analytic function of a given function? So the analytic function of which either real or imaginary part is known can be found by using Cauchy-Riemann equation. In the previous lecture, I have given how can we find the Cauchy-Riemann equation. In the Cauchy-Riemann equation, the two conditions is very important. First one is ux equals to vy, and the second one is uy equals to minus of vx. If both these two conditions satisfy, then we say that the Cauchy-Riemann equation is satisfied. Okay, so here to find the analytic function, let uxy be known and then we have to find v. So whenever we have to find some analytic function, then one function is given to you and another you have to find with the help of the previous one. Okay. So let us see how can we find the value of v. So dv can be written as del u by del x into dx and del v by del y into dy. And this is equals to Vx. We can write the del V by del x, the partial differentiation of del V by del x as Vx, and the partial differentiation of del V by del y as del y. And we can write it as Vx dx, Vy dy. Okay. So this is equals to, since Vx equals to minus of Vy by the Cauchy-Riemann equation, what we have here is Vx equals to, in the Cauchy-Riemann equation we have Vx equals to minus of uy, and therefore we will put this value to be here, and similarly Vy equals to ux, and then we put this value to here. So what we get here as the del v by del x becomes del u uy and del v by del y becomes ux. So our differential equation becomes dv equals to minus of uy dx plus ux dy by Cauchy-Riemann equation. Therefore, minus del u by del y into dx plus del u by del x into dy. Let us put this as equation number 1. From the equation number 1, we see that this is the equation of the form m dx plus n dy, which is the exact differential equation. So here first we find del m by del y. So what is del m by del y? Here the value of m, from comparing these two values, we get the value of m equals to del u by del y with the minus sign. So here we put del m by del y equals to del by del y bracket minus del u by del y, and by the partial fraction of this value we get minus del 2u by del y2. Similarly, del n by del x equals to del by del x of n. So this one is the value of n here. So we put this value here. So we get del by del x into del u by del x. And while differentiating partially with respect to x, we are getting del 2u by del x2. So here we use the condition of exact differential is del m by del y minus del n by del x. But here we will just write del n by del x minus del m by del y, and this is equals to del 2u by del x2 from here, and again del 2u by del y2. Since there is a minus sign, the minus minus becomes plus, so plus del 2u by del y2, and this value is equals to 0. Okay, since u satisfy Laplace's equation, in the previous notes I have given what is this Laplace equation. So Laplace's equation is if the partial differentiation of the second order with respect to x and the partial differentiation of function with respect to y sum becomes 0, then we say that the Laplace's equation satisfy for u. If we will write del 2u del 2v by del x2 plus del 2v by del y2 equals to 0, then we say that we satisfy the Laplace's equation. Okay, so here we say that for question number 2 that u satisfies Laplace's equation. Therefore, we can write like this: del 2u by del x2 plus del 2u by del y2 equals to 0. Here we put this equation as equation number 2. Why this happens? Because we see that if the differential equation is exact, then we have del m by del y equals to del n by del x. And here we use this condition, and that's why we have write it here: del n by del x minus del n by del y equals to 0. Okay, which is the condition of exactness. This is a very important exactness. Therefore, the equation 1 can be integrated. Now, both u and v are known as such that fx equals to u plus iv can be determined. And here what we get, z equals to u plus iv. And this function z will give the analytic function. And somewhere we can write like this: fx equals to u plus iv. And this will give the analytic function. Okay, so let us see some example. I have taken here the example, if u equals to e to the power x, x cos y minus y sin y, then find the analytic function u plus iv. So, as earlier I have told, whenever you have to consider the analytic function, then the one function is given to you, either it is u or v, and with the help of the Cauchy-Riemann equation, you will just find the another function v. So since here u is given, so we have to find the value of v. So for finding the value of v, we will use the differential equation like this. Okay, so now we have del v dv equals to del v by del x into dx plus del v by del y into dy. And by the Cauchy-Riemann equation, we have vx. Okay, what we have, uy equals to minus of vx. So we can write like vx uy minus times equals to vx. Therefore, we just write here minus times del u by del y in place of del v by del x. And again we have vy. And what is Vy? Ux equals to Vy. We just put the value of del V by del Y as del U by del X. So here we have placed the value of functions of V in the functions of U. This is equals to, now we will put the value here. So here we have U equals to this one. So while differentiating partially with respect to X and then Y. So first of all, we have to find the partial differentiation with respect to y. So here is the function of u. So let us differentiate partially with respect to y. What we get here is, since it is of the form u into v. Okay. That's why we have e to the power x bracket. Now x, first we're differentiating partially with respect to y. That's why we are getting here x sin y. X is taken as the constant. We differentiate partially the cos y and we are living with sin y. Then we have plus, since again it is a function of u into v. So again plus. Now sin y. Okay. So here what we see, again we differentiate minus y sin y. So while differentiating with respect to y, what we have here is y becomes 1 and we have sin y, and since there is a minus sign, that's why we will write here the plus sin y, and then plus y is taken as a constant, and now we differentiate sin y, so we are remaining with the value of sin y as cos y. So here we get the value as x sin y plus y cos y into dx. Here is a dx, so we just write here the dx. Now plus sign. Next value is del u by del x. That means we have to differentiate with respect to x. So now, since u is this one, so while differentiating with respect to x, what we write here, ux equal to, now e to the power x. So while differentiating to the power x, we get the e to the power x, and the same function we can write in the bracket. So this is x cos y minus y sin y. Okay, then we have a plus sign. Now e to the power x is taken as a constant. Now bracket. First value is x cos y. So the cos y is taken as constant. Now differentiating x with respect to x, what we get here is 1. So cos y into 1. Okay. Then we have minus sign. Now this is a function of y, so we cannot differentiate further because it is a partial differentiation. So we get the value 0. So what we get while differentiating with respect to x, the value is e to the power x, x cos y minus y sin y, and then plus e to the power x cos y. So here is the value e to the power x cos y plus x cos y minus y sin y e to the power x into dy. Now we just solve the brackets. So e to the power x, x sin y plus y cos y into dx plus e to the power x cos y plus x cos y minus y sin y into dy. Okay. Now we put the value in the terms of the integration. Then how can we put the values in one place so that we can find the integration easily? So here we have e to the power x, x sin y. So I have taken here e to the power x cos y dy. That is this one, e to the power x cos y dy first, then plus e to the power x sin y dx, and then x sin y e to the power x into dx. So this one is put it in one bracket. Okay. And the next one, the left values are taken in one bracket. So while differentiating, what we see that this one is the differentiation of e to the power x into cos into sin y. Okay, differentiation of this value. So if we differentiate this value, then what do you get? You just put this two value constant, then you differentiate sin y, you get the cos y. So e to the power x, okay, into x into cos y, the first term you get. Thereafter, while e to the power x and sin y is taken the constant, differentiating x, you get 1. So here you leave with the value e to the power x sin y. So next is e to the power x sin y. The third one, now we put the value sin y as constant. Okay, and here e to the power x, and x is taken the constant. Now differentiating e to the power x. These two values taken the constant. Now differentiating e to the power x. So what we get here is e to the power x. So we get x e to the power x into sin y dx. So this one, these three values combined, we get d e to the power x into x sin y. Similarly, these three values combined form, we get d e to the power x y into cos y. And together, while differentiating this value, since we have dv here, so now integrating both sides, now we integrating here, now integrating here, what we get is v equal to e to the power x into x sin y. Now what we get here is, now dv equals to integration of d of e to the power x into sin y, first one, and then we have plus d of e to the power x into y into cos y. So while integrating both sides, we get the value as e to the power x into x sin y, e to the power x y into cos y. Okay, and the left side we get the v. So here we get this value as vu. So here we have the value of u, here we have the value of v, and we have to construct z equals to u plus iv. This will give us the analytic function. So let us construct z. So while constructing the z, we write this function as f of z equals to u plus iv. Now value of the u, let's put the value of u is e to the power x bracket x cos y minus y sin y plus I. Then we put the value of v is e to the power x, x sin y plus y cos y plus c. I have taken the e to the power x the common, so we will just put this value in the bracket. And then plus c, integration constant. Now this is equals to e to the power x into x cos y minus y sin y plus ix sine y plus iy cos y and then plus ci. Okay. Now e to the power x is common. So here we have cos y, x plus iy. I have just put it the value in terms of x plus iy so that in the final result, the whole value will be in the form of z, not in the form of x or in the form of y. Okay, that's why I have just taken the common values and put the value in the terms of x plus iy if possible. In the most of the question, you get the value in the terms of x plus iy while constructing the analytic function. Somewhere you are not getting such this function, then you write just whatever you are getting the value of u and v. So here we have the fz is equals to e to the power x, x plus iy is again taken a constant, a common. So we have cos y plus I sin y plus ci, and this will give the value of e to the power x, x plus iy. Now cos y plus I sin y we can write like e to the power iy. E to the power iy is equals to cos y plus I sin y. Okay, that's why I write it here e to the power iy. This is the exponential function and then plus ci. So this will give the value of x plus iy. Now e to the power iy and then here's x. So we'll just combine this value. So we are getting here e to the power x plus iy and then plus ci. So this will give the value of z e to the power z and plus ci, where z equals to what? X plus I y. So here we have a function, analytic function is of the form z e to the power z plus ci, that is fz. Here we have fz equal to z e to the power z plus ci. And this is the required analytic function for the given value of u. I hope you all understand it very well. If you have any doubt, then ask me. Thanking you. Thank you all.